Hello everyone, welcome to the class on NIPER 2020 paper analysis, and in this video I am going to explain organic concept tested in NIPER 2020 paper. The concepts which I am going to explain are basicity of the rings, aromaticity, electrophilic substitution and activating deactivating groups on aromatic compounds. And this is my channel. You just type in my name in YouTube, G Sai Rajesh, you will get the channel. Recently the channel has crossed 2000 subscribers. Thank you subscribers, and I have 126 pharma related videos. If you like the video content, do subscribe. Let's get into the class. Now the question is, arrange in the order of increasing basicity: piperidine, pyrrole, pyrimidine, morpholine. Now look at the question. This question is testing multiple concepts. So in one question you need to know, in order to get a correct answer, you need to know multiple concepts. One, you need to know how the basicity pattern is. You need to know the aromatic rings and carbocyclic rings and how it affects the basicity of the rings. So three of the concepts are tested: aromatic rings, what is basicity, and how the basicity will get influenced with the aromatic rings. Let us see one by one. Look at this. See, in order to determine acids and bases, we have three different theories are there. Arrhenius theory says that anything which releases proton is an acid, whereas anything which releases a hydroxy or OH minus is base. Now, the reason why we have different theories is it is because of the presence of solvent. In presence of aqueous solvents, Arrhenius theory works. If something is releasing H plus, it becomes acid. If something is releasing OH minus, it becomes a base. In case of Bronsted and Lowry theory, it is related to only H plus. If something is releasing H plus, it is an acid. If something is accepting H plus, it becomes a base. Now see, this can define acids and bases in solvents other than water. This is the reason why we have different theories. If you have a solvent as water, you can use Arrhenius theory. Other than water, you can use Bronsted-Lowry theory. The next one is Lewis theory. It says acids are electron, in fact usually it is electron pair acceptor, whereas bases are electron pair donor. See, this defines acids and bases without a solvent. Even though you don't have any solvent, you can just define whether it is acid or base. This is the significance between having three different theories. So in aqueous, non-aqueous and without a solvent, you can define whether it is an acid or base. So this is the concept. Now in case of organic molecules, we need to think about this one, Lewis theory. See, essentially all the theories are same. They will not contradict with each other. Let me give you one example. Take for the case of ammonia. Ammonia has got an electron, lone pair of electrons are there. Now, in aqueous solvents, like in place of protic solvents, what happens? Ammonia is converted to NH3, and here a proton comes and it becomes plus. This is given as NH4 plus. Loosely it is written as this. Now see what has happened. Now ammonia has accepted a proton. So according to Bronsted-Lowry theory, because it is accepting a proton, what is that? It is base, according to Bronsted. Right. Now look with the respective to electron pair. What is doing? When it is accepting a proton, it is donating its electron pair to proton. That is the reason why there is a bond formation. So what happens here? So ammonia is donating an electron pair. So this is, according to Lewis theory, it becomes a base. Now understand. See, according to Bronsted, it is base because it is accepting a proton. According to Lewis, it is a base because it is donating an electron pair. Essentially both of them are same. Take the other case. What is H plus doing? So proton donors are acids according to Bronsted. So this proton is donating itself to ammonia. So according to Bronsted, it is an acid. According to Lewis, what? This H plus is accepting this electron pair, hence there is a bond formation occurs. So according to Lewis also it is an acid. So essentially though they don't contradict each other. All the theories explains the same things. Now, if this is clear, we'll go to other things. Let us see about the rings and everything. Now see, first you need, once you are clear with the concept of basicity and acidity, then you need to know about these rings. Now what is this rings? This ring is piperidine. Piperidine ring is a 6-membered ring, saturated one. Now next one, let us see the other ring, pyrrole. Pyrrole is a 5-membered ring with a nitrogen, right? Let's see the other thing. Pyrimidine. Purines and pyrimidines are present in DNA. This is a very essential nitrogen base, and this is what is pyrimidine is. Right. Now the last one is morpholine. Morpholine again a 6-membered ring with oxygen and nitrogen at 1,4 position. So these are all the rings: piperidine, pyrrole, pyrimidine, morpholine. Now you need to check the basicity order among these things. Let us go one by one. Okay. Now look at this one. Let us see about this pyrrole one. Now pyrrole is an aromatic compound. Aromatic compound, it needs delocalization. See, all the nitrogens has got a lone pair of electrons. No doubt all of them has got a lone pair of electrons. Now what happens with this lone pair of electrons in pyrrole? The lone pair of electrons along with this adjacent pi bonds, they participate in delocalization. So what happens when you write the ring? Essentially what is happening is those two electrons are involved in delocalization and they will be revolving inside the ring. That means, does this pyrrole has got availability of electron pair? No, it does not, because it is involved in delocalization. When electron pair is not available, it will not be able to donate that electron pair and it cannot act as base. So basicity is very much reduced because the electron pair is not available. Right? So this is least basic. Right? Now the next one. Let us see pyrimidine ring. Now look at this. Pyrimidine ring, you have 2 nitrogens are there and 2 electron pairs are there. But what is happening is in pyrimidine also you have delocalized electrons are there. So though these electrons are there, inside you have delocalization of electrons are there. Now these delocalized electrons are essentially electron withdrawing in nature. So these electrons will be withdrawn towards the ring. So what happens? Again the electron availability gets a little bit reduced because of this one. Let us rank them accordingly. See, the least one is pyrrole. Let me give you a number called 2. The next one is this one, because though the electron pair are there, because of electron withdrawing nature of these delocalized electrons, the electron availability reduces. This is what happens. Now the next one, let us see about morpholine. Now morpholine, what is there? You have electron pair is there. Is it completely available? No. They have an oxygen which is electronegative than nitrogen, so the electrons are being pulled by oxygen. So the availability reduces, but still it is available. So let us rank it as 3. Now understand the differences between these two things. Here the delocalization has got very good electron pull because they are circulating all these places and they will be withdrawing electrons, whereas in oxygen it is only because of its electronegativity, so the available electrons are a little bit higher, so this one will be a little bit more basic. Now coming to piperidine, do you have delocalized electrons? No. So all these electrons are readily available to donate, so this one is highly basic. Now understand the concept. So the basicity we are defining with respect to electron pair or Lewis base theory. Electron pair donor is a base. Now the electrons are not available in case of pyrrole, so it is least basic. Now after that pyrimidine, though electron pairs are available, they are under the influence of delocalized electron withdrawing effect. Now in case of morpholine, oxygen will be withdrawing electrons, but the degree is little bit less. So this one, when you compare, morpholine is more basic than pyrimidine, whereas highly basic one is piperidine. So the least one is pyrrole, next comes pyrimidine, next morpholine, and then piperidine. So you need to understand the concept, then it will be very useful for any competitive exam. Moving further, now which of the following is not aromatic? Again you need to know these heterocyclic rings. Now thiophene is a 5-membered heterocyclic ring with sulfur. Now the next one is dioxane. Di means 2, oxa means oxygen, a 6-membered 1,4 oxygen containing ring. Next one is pyrrole. Just now we have seen what is pyrrole is, a nitrogen containing 5-membered ring. Now isoxazole. See, oxazole and isoxazole and oxygen nitrogen containing heterocyclic rings. In oxazole the nitrogen and oxygen are present in 1 and 3 positions, whereas in isoxazole they are present in 1 and 2 positions. So this is oxygen. So this is isoxazole. Now you need to find out which one is a not aromatic one. But before getting into that, let us understand what is aromaticity. See, in order to be aromatic, see, all the aromatic compounds show unusual stability, and this stability is because of resonance energy. Now, in order to be aromatic, the molecule should be cyclic in nature, and it should have conjugated double bonds, and the Huckles rule says that it should have 4n plus 2 pi electrons, and the molecule should be flat. Now, cyclic means it has to be cycle in form. Now, flat, let us understand this. This is also known as planar. When you see the benzene will be like this. This is what is meant by flat molecule or planar molecule. See, this will clear you the things. If this is a surface, you put this atom, it will be lying flat on this surface. That is what is planar or flat means. Now, conjugated means alternating double bonds. See, you have one double bond here, a single bond, and then a double bond, a single bond, and then a double bond. So, this is called as conjugated. Now, 4n plus pi electrons, n here, see 4n plus 2 pi electrons. Let us understand this. This is a Huckle rule. N is an integer. Integer means 1, 2, 3, 4 kind of thing. If n is 1, what happens? 4 into 1, 4, plus 2 is 6 pi electrons. So, in order to be aromatic, the cycle should have these many number of electrons. Look at benzene. See, each pi bond is made up of 2 pi electrons. So, totally how many electrons are there? 2, 4, 6. 6 pi electrons are there. So, it satisfies the rule of aromaticity. So, this is how you need to think. In order to be aromatic, it has to satisfy all the 4 conditions. Look at them. See, thiophene, it has got, these electrons are participated in aromaticity. So, what happens? The molecule is flat, it is planar, it satisfies 4n plus 2 pi electron rule, and conjugation is there. Alternating bonds, alternating pi electron revolving is there. The same thing with pyrrole. You have electron pair is there, all the requirement is satisfied. Oxazole is also there, oxygen electrons will be participating in conjugation. So, what is odd man out here? Dioxane. So, there is no conjugation is there, and no pi electrons are there. So, both of them are required to be aromatic. So, dioxane is not aromatic. Moving to the next one. Now, furan is aromatic. Again, furan is 5-membered oxygen containing heterocyclic ring. Now, it says furan is aromatic. What is the value of Huckle in it? Now, I explained you just now, Huckle says 4n plus 2 pi electrons. It has to be there. Now, n is what? An integer. Integer means 1, 2, 3, 4 like this. So, according to this, it should have 6 pi electrons. 6 pi electrons, look at this. See, this pi bond 2 electrons, this one 2 electrons, and these oxygen electrons are involved in aromaticity. So, this will be revolving inside the ring. So, how many are there? 6 electrons. So, according to Huckle, furan contains 6 delocalized electrons. So, answer is D. Moving to the next one. Now, under what reaction conditions does the electrophilic chlorination of aromatic compounds usually occur? Now, let us understand this. See, this is what is a benzene ring is. Now, benzene ring has got these things. Now, you know benzene formula is C6H6. It has got all these hydrogens attached like this, sp2 hybridized one. Now, usually in aromatic compounds, the characteristic reaction on aromatic compound is electrophilic substitution. Electrophilic substitution. Let us understand each by every part. Electrophile means which is moving towards an electron. Electrophile means like. It will have a positive charge. It will be going towards a negative center. Hence, this one is known as electrophile. Now, electrophilic substitution occurs. Why? Because benzene has got all these revolving electrons. It is an electron-rich compound. So, electrophiles will tend to move it closer because they are looking for electrons, and electrons availability is very high in benzene. Now, once it attaches, what happens is this proton comes out as, this hydrogen comes out as proton, and this electrophile attaches here. See, electrophile will get attached here. So, what has happened? This electrophile has knocked off this proton, and in that place, it has substituted. So, the substitution of hydrogen with an electrophile occurs, and the electrophile is getting substituted. Hence, it is known as electrophilic substitution. These are the characteristic reactions of aromatic rings. Now, the question is, what is the reaction condition? Now look at them. Again, it goes back to our acid-base theory. See, this chlorine acts as Lewis pair. Why? It can donate an electron pair, and aluminum chloride acts as electron pair acceptor, and it forms this one. See, usually chlorine is very electronegative atom. It will not leave its electron unless something is grabbed electrons. It cannot act as an electrophile. In order to be electrophile, the chlorine should lose its electrons. When it happens in presence of AlCl3. Why it is happening with aluminum chloride? Because look at this, aluminum atomic number is 13. So it has got 1s2, 2s2, 2p6 and 3s2, 3p1. This is what is electronic configuration is. Now look at them. We are concerned with valency shell. In the valency shell, it has got 3s2 and 3p1. This is s2 and 3p1. Now when it is excited, this is what happens. See, this is 3s1 and this is 3px, 3py, 3pz. Now what has happened in excited state? A single electron is present in these three orbitals, but an empty orbital is present, that is 3pz. This empty orbital can accommodate two of the chlorine electrons. This is what happens. They are essentially acting as Lewis acid. So when this happens, see, these electrons are accommodated by aluminum. What happens? It is generating chlorine electrophile, and that electrophile will binds with this. Finally, hydrogen is knocked out as a proton. Chlorination occurs. So what are the reaction condition in presence of AlCl3? So look at the options. This is what is the option. Again, you need to understand why aluminum is acting as a Lewis acid, because it has got an empty orbital is there. Answer is P. Moving to the next one. Now, which of the following is the strongest activating group in electrophilic aromatic substitution? See, just now we have seen on aromatic compounds you have electrophilic substitution occurs, right? Now, when the presence of group will sometimes activate electrophilic substitutions, and depend on the nature of the group, some groups will deactivate towards substitution. Now the question is, which one is strongest activating group? Now understand this, an electrophile comes with a positive charge and substitutes here. Now it is looking for electrons. So if this group is enhancing electron availability on the ring, then it will activate the ring towards electrophilic substitution. So you need to identify the group which will donate electrons to the aromatic ring. Look at them. OCH3. Oxygen has got electron pair. So these electron pair can be donated towards ring and it can activate the ring. But let us see the other options. Now in nitrogen, you have a lone pair of electrons are there. Again, these electrons can be donated. Now see, both of them can donate electron pairs and activate the ring. But which one is the strongest one? When you compare oxygen and nitrogen, oxygen has got high electronegativity. That indicates the ability to keep the electrons with itself is very high because of its electronegativity. Whereas nitrogen has got low electronegativity, so it can easily donate electron pair. Now apart from that, look at this. Nitrogen is attached with two of the methyl groups. Methyl groups are electron donating in nature. So nitrogen can easily donate electron pair. Again, methyl are electron donating in nature. So the donating ability of this electron pair increases. So this one is very strongly activating. Now let us look at the other options too. Now the other options, see, COOCH3. This is what is given as CO2CH3. Now look at this. See, to benzene ring, this carbon is attached and this carbon is attached with oxygens. Oxygen, very good electronegativity, it will be pulling electrons. So from the carbon, electrons are going away. That means from the ring, the electrons will be pulled away because the carbon is essentially acting as electron withdrawing. So this one in fact deactivating group. Now nitro 2, the same thing. Nitrogen is attached with oxygen. When you compare nitrogen and oxygen are more electronegative. So when the ring is attached with this kind of group, it is essentially acting as electron withdrawing. So both these groups will reduce electron availability. Both of them will increase electron availability. Out of them, this one is highly strongly activating group. So the answer is this one. In fact, there is a list. Take a screenshot of this. These groups are called as activating and orthoparadirecting. These remaining groups are called as deactivating and metadirecting. Now the last one. Now Friedel-Crafts reaction is observed in, look at this, nitrobenzene, aniline, both of them and none of the above. So this is a tricky question. You need to understand the explanation. See, a benzene ring is deactivated by strong and moderate electron withdrawing groups. Nitro, just now we have seen. What is the question asks? See, nitrobenzene. Can you observe Friedel-Crafts on nitrobenzene? No, because it is strong deactivating group, the reaction will not occur. In order to occur, you need to have an electron donating group. Second one, Friedel-Crafts reaction also do not occur with amine group because it reacts with AlCl3. See, this amine is reacting with AlCl3 and it is forming a deactivating group. Why? Nitrogen will be having a positive charge, so it becomes an essentially electron withdrawing. So here also the reaction will not occur. See the tricky thing, nitrobenzene no, aniline no. So Friedel-Crafts is observed with none of the above. You need to understand the reasons. Students can guess this easily because it is deactivating, but here amine is reacting with AlCl3 and no reaction occurs. So these are all the concepts which are tested in NIPER 2020 paper. Thank you for watching this video. If you like the video content, do subscribe.